Dear students, today I will discuss a new chapter, that is wave optics. So as an introduction to this chapter, wave optics. Here we treat light as waves. In the previous chapter, that is in ray optics, we have taken the light is traveling in a straight line between one point to another point called as a ray of light. But here we treat light as wave and wave front. The idea of waves and wave front we use. In fact, the light is an electromagnetic wave originating from a source in the form of particles, that is photons. But when it travels in a medium or in vacuum, it propagates in the form of electric and magnetic field oscillations or vibrations, even in the vacuum. Light can travel even in the vacuum also, and light travels fastest in the vacuum, that is with the speed of 2.9979 into 10 power 8 meter per second. The speed of light is denoted by the symbol C, 2.9979 2458 into 10 power 8 meter per second. This is the speed of light. And the wavelength of visible light, it's a range from where to where. So it is approximately 400 nanometer to 750 nanometer, or we can also write in terms of angstrom, 4000 angstrom to 7500 angstrom. But while substituting the values of wavelengths, we substitute in the meter. So that can be written as 4 into 10 power. Conversion, 1 angstrom equal to 10 power minus 10 meter, or 1 nanometer is equal to 10 power minus 9 meter. If you make use of these substitutions here, the wavelength range of light in meter we can write, 400 into 10 power minus 9, 10 power 2 here, 10 power minus 9. So 2 minus 9 is minus 7. So we can write 4 into 10 power minus 7 meter to 7.5 into 10 power minus 7 meter. So this is the approximate range of wavelength of visible light. The light within this wavelength is visible to us. The other radiation, maybe 300 nanometer or 900 nanometer, is not visible to us. The wavelengths of light or radiation, electromagnetic radiation, less than this wavelength, 400 nanometer, falls under ultraviolet radiation, whereas the wavelength beyond this right side, greater wavelength or more wavelength than 750 nanometer, falls under infrared radiation. So longer wavelength to visible light is infrared radiation. Shorter wavelength than visible light, another side, is ultraviolet radiation. So this is the visible region of the light. This is the wavelength range for that visible region. And then there is another term called frequency also. So while substituting the problems, the wavelength you have to substitute in nanometer like this only. Convert nanometer or angstrom into meter. Only the last one we have to substitute. A particular wavelength, maybe 600 nanometer of light they may give. You have to take 6 into 10 power minus 7 meter in the numerical problems. Then there is another term called light, that is frequency. Speed is this much, and this speed we can take approximately 3 into 10 power 8 meter per second for all calculations. 3 into 10 power 8 meter per second for all calculation. This is in vacuum. This is in vacuum. I am telling in vacuum. And in any other medium, the speed will be less than this. So light travels fastest in the vacuum and other media it will be slower. In air it is slightly slower, but approximately 3 into 10 power 8 meter per second we can take, and in glass it will be approximately 2 into 10 power 8 meter per second. In water it is 2.25 into 10 power 8 meter per second. So like this the various numbers, speeds of light, and wavelength also changes, but the frequency, whenever light travels from one medium to another medium during refraction, the frequency value remains the same. Frequency is unaltered during refraction. So once the light is emitted by the source, the same frequency light is traveling in various media. Okay, so that's about the introduction part about this, and various theories of light I will discuss now as given in the textbook in the introduction part. Okay, so various theories of light, okay, various theories of light. So the different theories given by various scientists regarding the nature of light. So it is now we know that it is electromagnetic wave during propagation, and it is emitted as a particle, or it is absorbed as a particle during a phenomenon like a photoelectric effect. But when long ago the scientists or the pioneers who done a lot of experiments in the optics, they tried to explain the nature of light. So firstly the Descartes, okay, the scientist was Descartes, and later it is Newton modified this theory. Descartes and Newton modified a theory called corpuscular model of light, okay, or corpuscular theory. So according to this model given by Descartes, light is emitted by a source in the form of tiny particles called as corpuscles. So corpuscles are the tiny particles which are actually making the light. Tiny particles. Now we have anyway named as photons, but the idea of Descartes may not be exactly that. So that is corpuscles, small particles. So light is composed of small particles called corpuscles, which are emitted by a source. By that time, the source may not be light like this. May not be a bulb, may not be a lamp, or may not be a torch. It may be a firewood, or it may be even, it may not be a candle also. In the years 1600 to 1700s, so when the people were doing experiments, the natural source of light was only one, that is sun, and the artificial sources may not be that many as we have now, so many. Here light emitted by certain source, maybe burning of some firewood or any other substance, gives rise to light. Okay, so lamp, we up the lamp, all that we have. Okay, so now this source emits the light in the form of tiny particles. Okay, so that different sized particles gives the different colors of light. So that's the idea given by Descartes' model, and later developed by Newton. Different sized particles gives rise to different colors. So okay, so different colors are because of the different sized particles. So how to distinguish the colors? So that's the idea. Okay, then later on drawback of this theory, or we can say disadvantage or drawback or failure. Okay, so that is nothing but during refraction. So whenever light travels from a rarer medium to denser medium, its velocity increases. That is the idea, or that is the concept explained in this theory. Okay, that is the hypothesis, I can say. But that idea is wrong. Absolutely, it is wrong. Later proved by a scientist called Foucault. Okay, Foucault experiment proved that. Okay, Foucault is the name of scientist who proved that light in a denser medium travels slower. In a denser medium, light travels slower. Like in air, it is faster, and if it is moving from air to glass, the speed of the light decreases. It moves slower. The speed I said 2 into 10 power 8 meter per second approximately. Because the speed of light in any medium depends on the refractive index of the medium. Refractive index, optical density. And Foucault showed that light, when it is traveling in a denser medium, it travels slowly. Its velocity or speed decreases. According to Descartes or Newton's idea, according to this model, corpuscular model, light in denser medium travels faster. So that idea is absolutely wrong, as proved by Foucault. Hence this theory is rejected. Then later, the next theory comes into picture. Okay. So second theory is given by Christian Huygens. So famously called Huygens theory. Huygens wave theory. Huygens wave theory of light. So according to this Huygens wave theory, light is a longitudinal wave. Light is a longitudinal wave according to this theory. And there is a medium called ether, all pervading in the universe. Okay, so ether is the hypothetical medium. There is no exact evidence for this medium, existence of this medium. Okay, so light travels in the form of longitudinal wave through entirely spread ether medium. Everywhere in the universe there is a medium called ether spread over. So that is the idea of Huygens wave theory. So it is given by Christian Huygens. Huygens, name of scientist. Okay, so the longitudinal wave, idea of longitudinal wave, we have studied in first year also, longitudinal waves and transverse waves. Sound waves are actually longitudinal waves, and you have studied light waves are transverse. But this scientist, Huygens, says that light is a longitudinal wave, and we know that for a longitudinal wave propagation requires medium. So for that he assumed all pervading medium, means entire universe there is a medium called ether which is spread. And later again experimentally it is proved that there is no such medium exists. So existence of the medium called ether is absolutely wrong. There is no medium called ether is present. So no such medium exists. Hence this theory again fails. So Huygens wave theory failed. Okay. So this is the main drawback here. The assumption of the hypothetical medium ether is proved it is not there. Such medium is not there. And longitudinal wave also, it is absolutely wrong idea, because light is a transverse wave found later. Okay, not by the time of Christian Huygens. It is found that light is a transverse wave after a few more years. Okay. Then comes the another theory. Okay. The theory is electromagnetic wave theory. Electromagnetic wave theory. So it is given by electromagnetic wave theory given by James Clerk Maxwell. James Clerk Maxwell. So the scientist Maxwell, a very famous scientist, and has given this expression for speed of light 1 by root of mu naught and mu naught into epsilon naught, speed of light, and this number comes to nearly 3 into 10 power 8 meter per second in magnetism and electrostatics. You know very well about these numbers. Mu naught 4 pi into 10 raised to minus 7 and epsilon naught is 8.894 into 8.854 into 10 power minus 12 farad per meter. These two numbers, if you substitute, you get it. So this is the expression given by Maxwell, and with the help of set of equations connecting electricity and magnetism. Electricity and magnetism are interlinked, they are interrelated, and later the scientist called Faraday has done so many experiments on this electricity and magnetism interrelation. So this scientist James Clerk Maxwell also linked the concepts electricity and magnetism, and with the help of some equations, okay, those equations are mentioned in the textbook. Okay, so with the help of those equations he described the electromagnetic wave nature of light. Electromagnetic wave. So light is an electromagnetic wave. So light, while propagation, has two types of oscillations. One is electric field oscillations. In the perpendicular plane, magnetic field oscillations will be there. So electric and magnetic field oscillations, vibrations, will make the light propagation, and they are vibrating in or oscillating in a mutually perpendicular plane, and the direction of propagation is perpendicular to these electric and magnetic field oscillations. So this is about electromagnetic wave theory given by James Clerk Maxwell. The drawback of this theory is that it could not explain the particle nature of light. So during emission and absorption, light behaves like particles. So no idea or no information or explanation given by James Clerk Maxwell in this regard. So the next model comes quantum theory of light given by Max Planck. Max Planck has given the theory called quantum theory. Okay, Planck's quantum theory of radiation. So one important formula he says E equal to mh nu, or h nu also enough. So energy of the light photon emitted, or it may be absorbed also. So it is h nu. Energy of the light photon emitted by source equal to h nu. We can write h nu as hc by lambda also. Okay, so nh nu, where n is any integral number 1, 2, 3, etc. So energy of a photon emitted by some source is always multiple of h nu, or product of Planck's constant and the frequency of the radiation. So, okay, you can write in terms of wavelength also, hc by lambda also you can write. So this is the quantum theory of light. Whenever light is emitted by source, it exhibits or it behaves like a particle. It emitted by source behaves like a particle. But while propagation, according to electromagnetic wave theory, it says light is an electromagnetic wave. It has got electric and magnetic field waves. So electric and magnetic field oscillations, vibrations. So in the form of electric and magnetic field oscillations, the light propagates from one point to another point. So this is the basic idea. And then comes another scientist called Louis de Broglie. He combined this theory because light in some phenomena, it behaves like waves, like in interference, diffraction and polarization. Light behaves like waves. Whereas in phenomena like photoelectric effect, black body radiation, Compton effect, all that, light behaves like particles. So now there is a confusion whether we have to take light as a particle or we have to take light as a wave. So the Louis de Broglie suggested light can behave like particles sometimes, like emission or absorption, and some other time it can behave like waves. And he extended the idea of this particle and wave duality, wave particle duality, to the particles like electrons, protons, neutrons. Okay, for that particles also we can apply this wave particle duality, because they are particles. Under suitable conditions, the electron, proton, neutron, all that, whenever they propagate, they exhibit wave nature. So this is about the brief introduction part for this wave theory and some information regarding the optics. Now I will go to the wavefront, concept of wavefront. So briefly I will explain wavefront means what. So wavefront. Okay. So wavefront means, suppose one example I will. If you drop a stone to a calm pond, okay, so what happens? The ripples start from or origin from the point where you drop the stone, and they advance in all directions for few minutes. After that it will stop. So what are those ripples? They are the waves actually. They are the waves on the surface of water. They are the transverse waves. We can say transverse waves. And now if you imagine, if you assume the crust portion, one line of crust you take. Crust is like this, it is. Not the entire portion, only one part you take. So this forms a ring shape. Okay, now that point, all points on that at the crust, at the topmost part of that ripple will be vibrating at the same phase, because you studied in a first year waves chapter. For any wave propagation there is a term called amplitude, there is a term called wave velocity, there is a term called phase. So phase, sine of omega t plus kx or omega t minus kx, cos of omega t plus kx or cos of omega t minus kx. We use those mathematical symbols, functions to represent the wave motion. So here the particles which are vibrating at the highest point on the crust form a ring shape. Okay, that ring, okay, I can take as a wavefront, because all the particles are vibrating in the same phase. Phase means state of vibration. Phase is state of vibration. Okay, so the particle here has the certain phase, and another little bit away, another particle is at the highest point. Okay, ring shape it is. Okay, so circular, we can see circular portion. So in that at the highest point you can observe that highest point will change as the wave advances on the ripples advance on the surface of water. What happens, that circular pattern will shift away from the source where it is produced. But that highest point, what you can say, at one moment we can say all the points on that highly raised part, they are in the same state or called as wavefront. So wavefront by definition, it is the surface of constant phase. Surface of constant phase. Only this much is the definition. Surface of constant phase is called as a wavefront. Surface of constant phase is called as a wavefront. Okay, so then Huygens idea is, so wavefront is a surface of constant phase. Now if you have a point source, okay, here is a point source, I have a small tiny bulb or LED, okay. Now when it is glowing, so the light is going in all directions. It is not only this way, it is going in all the directions, 3 dimensions. So it going this way also, this way also, this way also, this way, all around it goes. So at one point, at particular time instant, the waves originate from this bulb, with this source, they travel, so in the form of electromagnetic wave. After a small time, very small time, the light is here and another one will be here. So if you join those surface, those points on the different waves, you join, okay, so that you are joining all the points which are having the same phase. So then we get a spherical wavefront. So the idea is here, a point source, the waves will advance like this, okay, in all around it goes. Okay, like this. So if you join a surface, we get a sphere. Okay, so then we get a spherical wavefront. The idea is this much only. Important is from a point source, we get a spherical wavefront. If the source of light is a narrow slit, or it may be a narrow lamp, a thin line, that kind of source, then it is a linear source or line source. Okay, so that giving rise wavefront we have to get. If I join the surfaces all around, it goes like this. If I join a surface which are vibrating in the same phase, okay, so then I get a cylindrical wavefront. The surface which is having the same phase, same state of vibration in all the waves. So it is not only going right and left. We assume it is 3 dimension. So this is the line source. Light is going this way, inside, like that. All around it goes from a line source. Okay, like this. This is the source of light. So light waves are going this way, all around. So if we join all the surface, all the points to get a surface, all the points which are having same phase, then we get a cylindrical wavefront, and that cylindrical wavefront will advance. In all the directions. This way it advances all the way. Okay, so then we get from a linear source, line source, we get a cylindrical wavefront. From a point source, we get a spherical wavefront. Now at far distance, what happens? This wavefront is almost a plane surface. Okay. So at infinite distance, it is at the small distances, point source gives rise to spherical wavefront, and a linear source gives rise to cylindrical wavefront, and at large distance, a point source or a line source, both. A point source or a line source gives rise to a plane wavefront, a plane surface. The wavefront is a plane surface. We get a plane wavefront from both point source as well as a linear source at far distance. For example, if you receive light from the sun or from other stars, so what happens? The wavefront coming, and here wavefront from the sunlight, we can treat it as a plane wavefront. Wavefront obtained from sun here on our surface is a plane wavefront. If it is a bulb, it is a spherical wavefront. If it is a very narrow, thin fluorescent tubes, commonly called as tube light, very thin if it is, so then I can get very near to that tube light or fluorescent tubes, I can get a cylindrical wavefront. From the sun, where in this place on the earth surface I get a plane wavefront. So at far distance, both point source as well as a line source gives a plane wavefront, because the waves are almost parallel. Moving. So at any point, if you join the waves which are having the same phase, will be the plane surface. It forms a plane surface. So that is the idea about wavefront. Next comes Huygens theory. That is Huygens idea of wavefront, and the statement about the Huygens principle. Okay. So Huygens principle is that Huygens principle, I will continue in the next class. Okay.